So this is the answer key, if you will, for the homework. I'm not going to write out all the questions, but because they've been done before, basically, just looking over them and see whether we can explain them. The key thing here. Sorry. So, Rutherford's gold foil experiment hypothesis is that all the alpha particles pass through the gold atoms. Okay, so first we should probably explain what it is. So, explain, you have to say that alpha particles were shot at a thin gold sheet and deflections were measured using some kind of detector. So the hypothesis was there would be zero deflection, all the alpha particles would pass straight through. The actual results were there were most of them passing through with no deflection, but very few had minor, major deflections, and very rarely you had a 180 deflection when the alpha particle bounced right back. What conclusions were drawn? This did not validate the blueberry pudding model of the atom. It instead gave rise to the hypothesis that the atom was mostly empty space because the alpha particles would pass right through, but there was a highly charged, very dense, positively charged center for the atom called the again, the term nucleus didn't arise until much later, but there was a highly dense, positively charged center to the atom where all the charge was concentrated. It was very small, and this is what the alpha particle, after it hit this, it bounced right back. So that was what that provided the explanations for this experiment. State Bohr's contribution to Rutherford's model. Bohr's contribution was basically the quantization of shells. We know that charged accelerating particles continuously emit energy, so the electron, if it was orbiting the nucleus, had to emit energy. And continuously emit energy, and therefore the atom would collapse, but this does not happen. So Bohr said that electrons are allowed in certain shells with discrete energy levels, we can say, or energy levels which are integral multiples of some value. And this, he said that the electrons in these shells do not emit energy, and therefore he helped solve that problem. Well, I mean, he provided a hypothesis to help solve that problem. So how did Bohr's model explain the emission spectrum for hydrogen? The emission spectrum for hydrogen consists of 4 lines, and Bohr said that these 4 lines correspond to the jumps between specific shells in hydrogen. For example, if the for an electron fell down from a 3 shell to a 2 shell, this would release a specific amount of energy because the energy level of the 3rd and the 2nd shell were fixed, and we could see that line as hydrogen. There was no intermediary emission spectrum because the electron had to fall from 3 to 2, 4 to 2, 5 to 2, 6 to 2, and there was no other transitions possible. And this kind of exact, precise energy difference it helped provide evidence for Bohr's model, because he said that the orbits had specific energies. What experimental evidence was a limitation? This is the emission spectrum for other kinds of gases like neon and helium, where there were not exactly 4 or a set number of transitions, there was multiple very close to each other, which kind of did not support Bohr's model. State the difference between orbits and orbitals. Orbits are set paths, set 2D paths, I'd say, around the nucleus, where the electron is located in. Say the electron is located in the orbit. Orbitals, on the other hand, are mathematical functions that describe the 3D probability density of the electron around the nucleus. Or any version of those would be fine. State the 4 quantum numbers for the valence electron of Br. So let's take a look at Br. All you need to know is that Br would be a 4p5. So this p orbital is now looking like that. This could be considered to be the valence electron, the last electron. So I would say 4, n equals 4, L equals P, which is 1, ML equals -101, MS equals +½ or you could write -½ Polonium, where is polonium? I don't even know where that is. Oh, right here. That looks to be a 6p4. So n equals 6, L equals P, which is 1, ML equals, so 6p4 looks like that. Because we go 1, 2, 3, 4. So the last electron went into here, so you're going to pick the -1, ms of -½ Just the way I draw things, you could write +½ as well, realistically. It does not matter there. Zirconium, I think that is. Zirconium is a 4d2. N equals 4, L equals D, which is 2, ML equals, because it's a 4d2, that means your d orbital is filling up like so. So -2, -1, and ms equals +½ You could write -½ as well. Radium is 7s2. So n equals 7, L equals 0, ML, there's only one value for that available, 0, and ms equals +½ or -½ because that's the last electron was the opposite, and we could have started with anything. Ce, it's over here, 58. 58 doesn't really help me. That is a 4f1. And I won't ask this on the test because, like I said, there was that confusion, but n equals 4, L equals 3, ML equals, for F1, it would be -3 because that's the first electron. And 1, 2, 3, 4, 5, 6. That's just -3 over here. The rest of them are empty. And ms equals +½ You could also write -½ Electronic configuration for magnesium and argon. So magnesium we know is 1s2, 2s2, 2p6, 3s2. So magnesium 1s2, 2s2, 2p6, 3s2. Argon we know has a 3p6 as well, so we're just going to add that. 1s2, 2s2, 2p6, 3s2, 3p6. That's the argon's configuration, because here we have 3s2 and then 3p6 for argon, because again, 3, this is the p block, so you get p6. There we go. Write the electronic configuration for these things. So again, we're going to use the short form. Let's see, where's tungsten? Right here. So this is a 6D, 1, 2, 3, 4, but it's not a 6D, it's actually a 5D, because we know that D you have to subtract 1 from the period number. So the ending is 5D4, so we'll go back to xenon. After xenon, there should be a 6s2, 4f14, because we go to the lanthanides, and then 5d4, we said. SB. Antimony, this is 5p3, so krypton. Go back to the nearest noble gas, is krypton, and we have 5s2, 4d10, 5p3. Rubidium, that's easy. That's just krypton 5. After krypton, you just have a 5s1. Then whatever Nd is. Neodymium, sure. So this one is over here. So we go back, still xenon 6s2, xenon 6s2. I think this will be a 5d1 4f. One, two, three, 4f3. There we go. Again, that one's confusing because depending on these ones are technically belong to the D block. They go over here, the lanthanum and the actinum. So they're the 5d1 and 6d1. And then after the D1, you suddenly switch to the F, and then you complete F1 to F14, and then you go back to D2. I don't know why. I have no idea why. It's just it's above my pay grade, so to speak, and well, certainly above yours at this point. Write the electronic configuration for chromium and copper. Okay, so chromium is argon 4s1, 3d5. Copper was argon 4s1, 3d10. So explain why they have different configurations than the regular trend. This is because one 4s electron moves or is excited, or you could just say moves to a 3D shell because the d orbital is half filled or fully filled, depending on which one you're talking about, making it more stable. Again, you have to say why it's more stable. This is due to high exchange energy and high symmetry. Alright, so that's the explanation for those ones. Fairly easy ones. State true properties of the S block elements. We know that they are soft metals, low melting points, boiling points, non-conductors. They have low ionization energies. These are fairly easy properties to mention. P blocks are harder. They have they're usually high ionization energy and relatively high electronegativities. D block, there's transition metals. They have metallic bonds, so they're usually good conductors, with some exceptions, of course, good conductors of electricity. High melting point, boiling point. Multiple transition states or oxidation states. F block, again, multiple valencies. You can say transition states, oxidation states. I don't think transition state is the right word technically, but the best term I think would be multiple oxidation states, since we've learned about oxidation briefly now. And form complexes. There are two properties of those. Some of those are radioactive, so half of them are radioactive. I guess that's kind of important to state, but half of them, not all of them. So, what is metallic bonding? So metallic bonding is the bonding that occurs in metallic solids. Example, sodium or iron. Again, not ions. No, it's just the bonding that occurs in the solid metal, which is just composed of atoms of that metal. So S block elements have low melting point and boiling point, while D block elements have relatively high ones. This is because melting point and boiling point has to do with the number of free, or the number of unpaired electrons that are allowed to be free in the lattice, because D block elements have more unpaired electrons to kind of let go of. They have higher melting points and boiling points than sodium, because sodium lets go of its one electron, but it has only one or two electrons to donate to the C. So that's what you would say. You'd say S block elements, or actually you would rather start with saying probably D block elements have more number of unpaired electrons than S block elements, and therefore they have higher melting points and boiling points, because the more unpaired electrons, the higher the melting point and boiling point. Explain why vanadium has the highest melting point in the 3D block and zinc has the lowest. Zinc has a 3D10 structure, and therefore this has no unpaired electrons, very stable, and therefore it has the lowest melting point. Vanadium has 3D3, which is the highest number, which has 3 unpaired electrons, which is the highest number of unpaired electrons in the d orbital, apart from chromium or manganese, which have 5. But because 3D5 is stable, the electrons are not as free as a 3D3 vanadium. So this is the highest melting point and boiling point, because this is the highest number of unpaired electrons that are completely free from the atom. Oxygen is more reactive because this is a 2p4, like so, and because it has 2 unpaired electrons, it wants to get a fully filled orbital, like so. Nitrogen has a 2p3, which is a half-filled subshell, which is more stable because of high symmetry and high exchange energy, and therefore it is less reactive than oxygen. S-block elements have low ionization enthalpies. P-block elements have high ionization enthalpies. S-block elements want to get rid of their S-block electrons in order to achieve noble gas configuration, and so the energy required to remove one of those electrons is not a lot. It's very easy to remove one of those electrons because they attain noble gas or stable configuration if you do so. P-block elements, realistically, they want to accept electrons in order to gain noble gas configuration. Taking them away is not leading them to a stable structure, or you have to take 4 of them away or a lot of them away, and so they have high ionization energies. Why do transition metals have multiple valencies? Because they have valencies is also some word you can use instead of transition states, I should say. That's because the d block unpaired, or the d orbital unpaired electrons are not very reactive, so they can some of them leave, some of them don't leave, and they're not really super what should I say? They're not super easy to take out like the S-block electrons, which, like, you know, sodium, that electron is ready to come or leave the atom and form sodium ion. However, D-block elements, the electrons like do it, they do it sometimes, they don't do it other times, and therefore that leads you to multiple valencies or multiple oxidation states. Alright, we'll cover the assignment, I think, in another video. Until then, I'll see you everybody in class.